Oleg Lavrentovich from Kent State will tell us about electrically driven dynamics of small particles in liquid crystals. This thing doesn't stay on.
Thank you. So let me introduce our research team. It's two graduate students. Oleg just finished his studies, and Laza Martinez, who just started. Sergei Shayanovsky is a visiting scientist in my group, and we did this work in collaboration with the group of Professor Jack Kelly, who is simulating, computer simulating the hydrodynamic effects in liquid crystals. So we are dealing with the simplest type of nematic. It's not the active nematic, it's not the pleiotropic nematic, it's just the nematic that is known in display applications. So it's the so-called thermotropic material. You hit a certain molecular crystal and it melts. First it melts into the nematic phase in which the molecules are parallel to each other, but they show no long-range positional order. And then at some somewhat higher temperature, you melt it into the true isotopic phase with no positional order and no orientational order. So as I said, the claim to fame for these materials is display applications. Some 80 years ago, Lavrentovich in the former Soviet Union discovered famous effect, the so-called Frederick's effect, that when you apply electric or magnetic field to the aligning slab of the liquid crystal, the molecules reorient because of the diamagnetic or dielectric anisotropy. And in late 60s, Jim Ferguson at Kent discovered that in a particular geometry of director orientation in the so-called twisted nematic cell, you can achieve a very good optical contrast if you would place the nematic cell driven by electric field between two polarizers. And that gave rise to all the wonderful informational displays that we are using nowadays, sometimes without realizing that most of them are working on the very same principle of the twisted nematic cell or somewhat modified cell. By the way, at that time, it was astonishing that between December 30th, 1969, when he put the scheme in his notebook and the first commercial product that he produced with his startup company, Elisco, in Kent, we had just about 11 months. So today I'll be talking about something that is somewhat different from the majority of talks here, which are concentrated on, let me say, collective behavior or hydrodynamic behavior of swimming of relatively complex particles or their groups in a relatively simple fluid, which is isotropic fluid. In our project, we are starting to look into the motion of relatively simple particles, and I'll be talking exclusively about solid spheres, but they are swimming in a complex medium, a nematic liquid crystal. So that allows us in some cases to direct the motion of the particles, and also it adds new levels of complexity, because in our case, in addition to the velocity field, we also have the director field that shows the orientation of the molecules, and we also have the electric field that can realign the director field. And the subject of interest, as I said, will be a sphere, a solid sphere, and at the surface of any material in contact with the liquid crystal, an isotropy of molecular interactions result in the so-called anchoring direction. And in our case, experimentally, we always achieve a situation when the liquid crystal director wants to be perpendicular to the interface. So if you have a sphere, you have a kind of hedgehog around the sphere. So what would happen if you would throw this sphere into the uniformly aligned nematic liquid crystal? Obviously, the far field, which is uniform, has to be somehow matched with the radial distribution around the sphere. And in most cases, the compromise is achieved by this configuration that was described in details by Tom Lubensky and David Weitz at that time at UPenn about 12 years ago. So what you have here is an elastic dipole. You have the radial configuration around the immersed sphere, And then in order for it to be matched with a uniform far field, one has to create an additional distorted configuration, in this case a hedgehog point defect, so-called hyperbolic point defect, shown on the left. Topologically, it kind of simply means that you balance the +1 topological charge of the sphere, the radial configuration, with a -1 topological charge of the hedgehog. And since the surface conditions at the sphere introduces these director distortions, you have a situation when you modify the colloidal interactions in the nematic fast just because of the elastic distortions of the field. For example, you can show that these elastic dipoles will try to attract each other along the line to form chaining, and that was shown experimentally. So in experimental cell, if you just throw these particles, if the original orientation is horizontal, you can easily understand that you might have 50% of the particles that create the hedgehog on the left-hand side, and 50% that would have this hedgehog on the right-hand side. So you would have left and right levitating, left and right dipoles. Another thing, if you would take a three-dimensional microscope that shows you director orientation in three-dimensional space, and we developed such a microscope to study phenomena like I am talking about today, you would also see that the particle, this dark disk, is kind of levitating in the bulk. It's not dropping at the bottom, despite the fact that it's somewhat larger than the typical colloidal side. It's about 4 or 5 micrometers in diameter. And so the reason is, again, the nematic nature of the material. What you have here is that the force of gravity that pulls the particle down, because the particle has a density that is about 2 times higher than the density of the liquid crystal, and that one is close to the density of water. So this gravity force is being balanced by the elastic repulsion between this dipole, the distortions around the particle, and the wall. The wall, the surface anchoring is planar, in-plane alignment, and it doesn't want to see any director distortions nearby, so it creates the force that pushes the particle up. And you can develop a simple model using the image forces, and you would realize that for typical sizes, let's say 5, 10 micrometers of the particles, this elastic force is sufficiently strong to overcome the gravity force, and you can then measure, for example, as the function of the cell thickness, how far away from the middle plane the particle would shift. And you would see that for relatively thin cells, the particle is almost in the middle of the cell, like for this 20 micrometers thick cell. And it just stayed there. It's interesting that if you make your particle bigger, then it would levitate even better, because the elastic force goes as r to the power of 4, and the gravity is obviously proportional to the wall. So what would happen now if you would reorient the liquid crystal as Fredericks did in his experiment? So you just apply electric field. In our case, it's directed from top to bottom and then from bottom to top, because it's an alternating field. We are not dealing with any ionic motion in this case. It's purely the electric anisotropy effect. Of course, you break the symmetry of the director distortions, and it turns out that, as you see from the slide here, the particles which are dipoles start to fill this. The right dipoles move to top surface, and the left dipoles move to bottom surface, simply because of the S-type of distortions in the cell. And then, if you recall a number of previous talks about the nematic hydrodynamics, it was stated that when you have a shear, that shear flow would align the liquid crystal. There is an opposite effect. It's that when you reorient the director, it creates a material flow in the cell. And the symmetry of this flow is such that in the center you have zero flow, but above the center and below you have increase in the velocity as shown here, and then at the two solid boundaries you have a no-slip boundary condition, and the velocity is 0. So, and this simple double symmetry breaks the configuration in the cell, and when you watch what these particles do, those of them that have the hedgehog on the right move into one direction, and those of them who have the hedgehog on the left move into the opposite direction. Those are the very same particles. It just happened that when they were thrown in the matrix, they acquired this left or right satellite. But then when you apply the field and driving the director back and forth, they start to move, and they move strictly according to their polarity. And you can play different. Well, before you start playing games, you would like to understand whether you have the phenomenon understood correctly. And for that, we just used the simplest model, namely the hydrodynamics of the electric crystal that is driven by the electric field. So what you have here is the director reorientation. That is the angle between the director and some axis, let's say the vertical axis that is z-dependent, this angle theta. And then you have the balance of torques. One is the elastic torque that is entering the G sub theta. K1, K2 are the elastic constants. And also the dielectric torque that reorients the electric crystal. And you have also the hydrodynamic contribution to the torque. So the second equation is the linear momentum balance equation. And you also can find in literature the values of all these viscosities, alpha 1, alpha 2, alpha 3, for the given material. And then you start simulating. You throw away, by the way, the particles, because the idea is that since the velocities are not that high and since the sizes of the particles are small, you're dealing with no inertia regime, low Reynolds number regime, and the particles just passively follow the flow. And so then you calculate what would happen if you apply the field. And we are focusing on the z coordinate that is close to the top plate and close to the bottom plate. You see that after you apply the field, the velocity profile requires this non-monotonic force. The reorientation forces the flow, and then it decays. And if you switch the field up, you have a relaxation, and you might notice that the velocity here is much smaller because this is the passive relaxation according to the boundary conditions at the substrates. And the most interesting thing is that if you now take the entire cycle and calculate director dynamics, you would realize that the velocity, the net velocity over the cycle is not zero. And then you match your computer simulations with the experimental results, and you see a very classic non-monotonous dependence of the velocity, net velocity of the particles, on the frequency of pulses that you send with your voltage generator. And it's easy to understand why it became in this way, because low frequencies, you just on the system with the number of pulses that are increasing when you increase the frequency, and at high frequencies, the system simply doesn't have time to react to frequently going pulses, and just decreases the velocity. So you can study jamming in this configuration, because if you decrease the particle, then the particles, if you decrease the thickness of the cell, the particles start to jam, and you can have interesting fractal dependencies here. And finally, what we are doing right now is, instead of acting on the background, we are acting on this very distorted region around the sphere. And as you might see, this might be something that you can call the simplest swimmer. It's not three spheres, it's just one sphere, but it swims in the nematic electric crystal rather than in isotopic fluid, and it can propel itself. Thank you very much.
Thank you. Other questions?
How is that propelled?
You apply electric field, but you apply it in such a way that you do not disturb the far field background. Remember, the sphere creates director distortions around itself to match the otherwise uniform director field far away. So most of my talk was about disturbing this far field, and the sphere just moves along. The last slide was about a configuration when the far field is not disturbed, but this distorted region is being addressed with the electric field. And
so just two probe wires, or?
It's the same. It's electric field, two electrodes, and you apply voltage back and forth, and that's it. It's symmetric with time average equals 0. But because of the broken symmetry of the system, the difference between the head and the tail, which is sphere, and the hedgehog, you have the net propulsion in the nematic crystal. It wouldn't happen in the isotopic.
So you have like a resonance frequency of like 5 hertz or something.
Right.
Is there a way to speed that up for the conditions? Where they move it and does it move
Yeah. Yeah, there are some regimes in which you can speed it up to, let's say, 10 micrometers per second.
Any other questions? Okay. Thank you. Okay, so the last talk is by Patrick Underhill from Rensselaer Polytechnic Institute, and he's going to tell us about velocity and stress correlations in suspensions of swimming microorganisms, theory and simulation.
I'll try and figure out how to get it so that it actually shows up the whole thing and not just right side of it.
Yeah.
So,
Put that in your pocket.
So I'm in the chemical engineering department at RPI, and I guess sort of in most of the research I do, hydrodynamics plays a pretty key role. So I'll be talking about some of the hydrodynamic effects in the correlations in swimming microorganisms, and we've heard a number of talks about that, so I'll skip quite a bit of the motivation. But in addition to sort of what leads to the collective behavior, I'm also interested a lot in the biological sort of relevance and impact of these. So I'll first show you one experiment and describe it, and then I won't talk about it anymore because it's too hard for me to do right now. But it's sort of the final goal I sort of have in mind. So this is a real-time movie of E. coli swarming on an agar plate. So we're looking down on top of the plate of agar. So essentially what happens is, right, you take your suspension of E. coli and you put it down on this plate of agar. And first, sort of a biological thing happens, which is they sense something about their environment. We don't really know yet what it is. And when they grow, instead of dividing, they don't divide anymore. They just keep getting bigger. And they have more and more flagella. And then once they are in that state, which is called a swarming state, you see these patterns. And as you've seen probably as this loops, the front of this group of E. coli is moving. So that allows them to very rapidly fill this entire plate of agar. And so perhaps this has some biological relevance in terms of sort of invasion of different regimes as sort of the bacteria are trying to, say, invade your body or something like that.
Everyone gets bigger this time?
So,
Are they eating?
So they are eating and they are dividing, but right, this is in real time, so you're not this is not driven by sort of their growing, right, because you're looking at it over a pretty short amount of time. But before this happens, they do have to grow and get larger and get many more flagella. So these are just the body, right, that you see of the E. coli, and it's pretty densely packed. And the flagella are sort of all intermingled, and it's kind of amazing that they can actually move with their flagella being so sort of tangled up. So that's the last I'll say about that, and move to a much simpler geometry. And so what I'll be talking about is correlations in these suspensions of these swimming bacteria. And so the two types of correlations I'll talk about are velocity correlations and stress correlations. Hopefully I'll get to sort of the end and say a couple slides about the stress correlations. So the velocity correlations, there are two types of velocity correlations. So suppose I have these two sort of organisms, right, which have label 1 and 2. So there's some direction that it's trying to swim in, and then there's some velocity that it actually goes in. And those are not necessarily aligned. And then there's another sort of swimmer with some orientation and some velocity that it goes in. So I'll be talking about the orientational correlations of how correlated N1 is with N2. Also, you can look at V1 and how correlated it is to V2. But this is also in a fluid. For this, we'll be talking about a Newtonian fluid. And so there's some fluid elements, say with some fluid velocity, and over here the fluid velocity might be like that. And so you can look at how correlated these fluid elements are as a function of their separation. You can also, right, as we've seen before, this active sort of motion of these organisms induces a stress like this at this position, and there's another stress here at this position. And so you can look at the stress as a function of time or space and time, and then look at spatial correlations of the stress, and also look at time correlations of the stress. And so sort of one reason we're doing this is to try and quantify some of these sort of collective behaviors, like these swirling patterns. Rather than looking at them and seeing they're similar, we wanted to try and quantify them by using these correlations. So the velocity correlations, we're going to try and use to quantify this collective behavior. But these velocity correlations can also sort of be related in some level to maybe the short time 2-point microrheology. So suppose you are doing 2-point microrheology, which essentially you track the motion of two probes that you put in. At short time, this probe might be going in that direction and that probe in that direction if they're being advected by the fluid. So we're neglecting sort of the Brownian motion right now of those probes. And so at short time, these velocity correlations will tell you something about the 2-point microrheology. Recently, there have been some theories to look at sort of the long time behavior of, or the spectrum of the 2-point microrheology and how that is related to these stress correlations, which is why, in particular, we are interested in that. So this is sort of the simplest model that we use to do our simulations and our theory. And so I might just say a few words about this since it's a little different, but similar to what we've seen before. So the simplest model that we have is to take this, say, organism, for example, E. coli or B. subtilis, and represent it by two beads connected by a rod. So this is very different from, say, what Aparna was talking about, because these two beads are the same size. And so if you looked at sort of Aparna's swimmer, that wouldn't swim, whereas this does swim, which might be kind of odd, because it's totally symmetrical. And so I want to sort of describe how that works pretty briefly. So essentially we treat the body of this organism as a sphere. This is sort of a real sphere. So with an E. coli, the body of the organism is, say, moving to the right. And so if this bead on the right is moving to the right, it has to push fluid out of the way. Right? A sphere moving through a fluid causes a disturbance. So that's what this blue line represents, is the sort of disturbance in the fluid caused by this organism. Now, this back sphere, I draw it as a sphere, but it's not really a sphere in some sense. It acts like something which is not a sphere. So if you take sort of flagella, right, it's a helical filament which rotates, and that's what causes the motion. So suppose you just had a helical filament without the body of the organism, right? And you somehow apply a torque to it to rotate it. So it's going to translate through the fluid. So now, suppose you tag or sort of attach to the front something that has to push through the fluid, right? It can't go as fast as it would want to. So it's going slower. So the disturbance it makes is as if it's going backwards. So it pushes the fluid backwards, even though it's going forwards, right? So that's kind of an odd, a sphere wouldn't do that, right? A sphere makes a disturbance in the direction it goes. But a helix can make a disturbance backwards, even if it's going forward. So that's why this the swimmer can swim. The flagella just pushes backwards, the body pushes forwards, and it sucks fluid in from the side. So hopefully that didn't just confuse you more. So then we basically, right, similar to what we saw earlier, if you have another organism over to the side, it will be evected sort of towards or attracted to this other organism. And so we essentially put a lot of these organisms into some domain and follow their motion. And I'll also mention sort of the effective volume fraction is the number density n times the volume of a sphere with length L over 2. So these two B's are separated by a length L. And so this is a movie showing sort of one of the simulations. I essentially, in these results, take a 3D periodic box, and I randomly place these organisms in there, and then I follow their motion in time. And I do that by writing down, neglecting inertia, so I write down a force balance. And then there's a hydrodynamic force, which is just a drag. It's minus a drag coefficient times the velocity of particle 1 minus the velocity of the fluid at the position of particle 1. And this fluid velocity is basically generated by all of the other organisms. Other than the swimming, it's a perfectly stagnant fluid. You're only getting fluid motion because of the swimming of the organisms. And so this, the way we formulated it, as sort of mentioned, sort of as a comment to Aparna's, the way we formulate this, we could do this as a pairwise additive calculation, but that still captures the multi-body hydrodynamic interactions, which is a slightly subtle point. And the other thing to mention here is that sort of in comparison to these local interactions that you might have, these are very global long-range interactions. And so we have to include every possible pair. And we do that in a very efficient way, which I won't get into. So here are the things I leave out, so I won't go into them. You can ask me later. It's a lot of things. So I'll skip that and just go to this. So we quantify the fluid structure by doing a fluid velocity or tracer velocity correlation function. So it's the fluid at some position dotted into the fluid velocity at another position r away. And we calculate that correlation as a function of the separation of the two fluid elements. So I have 3 different cases on here. The blue curve is if these organisms are not interacting at all, but they're still disturbing the fluid. So they just swim straight forever without sort of seeing one another. And they still have a fluid-fluid correlation, which is essentially most of it is captured by this black line, if you believe me for a second. And so that's another, if you're asleep, pay attention for this 1 second. So in contrast to some of these other correlations we see, you might expect to see like an exponentially decaying correlation with some correlation length. That's not what you see in hydrodynamics. Even if they are not interacting, there's no collective behavior, the fluid is still correlated with 1 over r correlations. Right? So it's a very subtle thing to measure the collective behavior. So if you have, as Aparna was mentioning, there are these pusher-type organisms and puller-type organisms. The puller-type organisms are interacting with one another, but that is not captured in this fluid-fluid correlation function. It's essentially the same as if they weren't interacting. But pushers do have some sort of larger correlation in the fluid. And that also increases with system size. So we have some finite size effect as we make the system bigger and bigger. And you can capture that with this theory. So asymptotically, you get this theory, which is 1 over r. That's the independent contribution. And then there's this finite size effect, which is the log order phi squared. It's a pairwise term. But it's logarithmic in the size of the system L over the separation. And using these two sort of fitting parameters, we get to see that sort of system size dependence. And I'll skip the stress correlations, other than to say that in our theory, we see a Lorentzian as a function of frequency. So a high frequency goes like 1 over omega squared, whereas experimentally, it goes like omega to the minus 1/2, and I don't know why that is. So I'll leave you with that and try to take any questions.
Thank you. Any other questions?
Or did I totally confuse you?
Over there?
You have finite size effects. If you change the size of your system, it changes the properties.
Yes.
What did you try doing periodic boundary conditions to simulate like that?
So, sorry I had to go through that so fast. So this is periodic boundary conditions. So I'll just put up the simulation. So it is periodic boundary conditions, where L is the size of the box. And so what we do is we say change the size of the box, but keeping the volume fraction the same. Right? So in principle, you'd want if
Size you meant
to
number of particles.
yes. So it seems like there's essentially infinitely large correlations in the system, which get cut off by this imposed periodicity. And as you sort of relax that by making your box bigger and bigger, you're allowing these correlations to get bigger and bigger and bigger. And those grow sort of logarithmically.
You said you wanted to include run and tumble dynamics.
Yep.
In a swarming system, do they still run and tumble, or do they just go straight and grow in big swarms?
It's not really clear, I think. So I think in some of these systems we could it might not be that important. So, right, if you have some organism which it gets reoriented because it is either moved by the fluid or hits another one, sort of before it has time to tumble, then the sort of run and tumble might not really play much of a role. And in sort of that experimental sort of the swarmy, they're sort of so concentrated and they're changing their direction so quickly that I think sort of the run and tumble might not be that important. So then it might sort of raise the question of, can they sort of chemotaxis, right? Can they, if the run and tumble doesn't affect their motion very much, then can they still move to, say, higher concentration or something?
Okay, so I think it's time now for the discussion period. We're going to shorten the discussion.